Our next speaker is Laurenz Wiskott, who will, I don't know if I can say it's similar perspective or different perspective.
Different perspective.
Different perspective.
And you use this one, I guess. So was this the... This was... So forward, backwards? Good. Oh, you didn't use it. Okay.
I always get confused with when I use this.
Okay. Okay. So, I want to apologize for my slides because my laptop died over the weekend, and I'm thankful to Toli who lent me his laptop for a few hours, so I could at least recover the figures, but there are no references, no text, no labels whatsoever. But I hope I will not confuse too much of it. I want to talk about a CRISP theory that is a theory that a colleague of mine in Bochum has developed, Sen Cheng, and sort of contrast this with a standard framework, and I think the two talks fit nicely to each other. So I first say a few words about this model. So the idea is we have cortical representations that go through the entorhinal cortex sort of as an interface to the hippocampus. The main site of storage would be a CA3, which because of its recurrent connectivity can be conceptualized as a Hopfield network, which is an auto-associative memory model. The dentate gyrus is meant to orthogonalize patterns, because if you want to store something in a Hopfield network, the patterns should rather be orthogonal to each other. And then CA1 is sort of a structure that helps sort of decoding the patterns again, but the actual storage and retrieval is done in CA3. So we call this a standard framework and not standard model, because there's not one model that actually represents this, but there's a whole series of papers by different people. We use here as a reference the model by Travis and Rhodes, and in particular by Rhodes 95. So that is one nice complete simulation of this that we use as a reference. So now, in contrast, the CRISP model proposed by Sen Cheng sort of poses that the association of, or the recall of individual patterns. So if you give a partial cue and this then gets completed to the full pattern that has been stored, that this happens in CA1 through heteroassociation. So you do auto-association, but you do this in a two-step heteroassociation process. So that's done here. CA3, the role of CA3 is to provide sequences. And here the idea is that the sequences are not stored in CA3. They're already there. So CA3 already has, by some self-organization process, sequences in there. And when you store a sequence, actually just associate the patterns that come from the outside, the stimulus patterns, to this already existing sequence. So that's what CA3 is there for. And dentate gyrus has a very similar role as in the standard framework. It's there to orthogonalize patterns and to disambiguate them, or to put them in context. And I want to talk about two models. So the one that concentrates on the single pattern recall, and the other one on the association of sequences. So this is work done by Thorsten Neher in my group together with Sen Cheng also. So here we use pretty much the Rhodes model 95. We have adapted it a little bit. So we have sort of the cell numbers are from red physiology scaled down by a factor of 100. Connectivity sparseness is taken from red physiology scaled down by a factor of 10. If you also scale it down by 100, there are no synapses left, so you have to scale down by less. Or there are too few synapses left. So this is number of neurons. Sparsity level is taken literally from what we know physiologically. So it's an attempt to sort of have an abstract model, but that respects some physiology. So black are shown connections that are fixed, and green are connections that are plastic, and they all follow sort of Hebbian type of associative rules. And it's pretty much exactly what Rhodes does in his model, except for that we've simplified the dynamics in some sense so the forward activation is just a linear sum over the weighted activities here, and then we have a k-winner-take-all mechanism to get the sparseness that we have in these different layers.
What is A exactly? What is
A is the activity level. So here 35% of the neurons would be active at any given time, here, etc. So these are two plots from the original paper by Rhodes, 95, and it shows the correlation of the recalled patterns as a function of the correlation of the Q. So if the Q is very poor, the recalled patterns are also very poor, but if you feed in perfect pattern, then the recall is good. And on the left side, and this is in CA3, this is in CA1, and this is in entorhinal cortex. On the left side, you see the dynamics with recurrent dynamics. So you have sort of the recurrent dynamics in CA3 actually working. And on the right side, it's the other way around. Without recurrent dynamics and with recurrent dynamics, and you see that the performance with recurrent dynamics is better, as you would expect, at least in CA3, also in CA1, but in EC, there's hardly any difference. So the quality of patterns that you recall in this model, so in Rhodes' model, in his original paper, the quality of the patterns in EC is pretty much the same, whether you use the recurrent connections in CA3 or not, which is a bit strange because the recurrent connections in CA3 are the essential concept here, right? But it doesn't make much difference in the output layer. Now we have reproduced this, so this is an attempt to really reproduce the results by Rhodes. Green means CA3 and red CA1, blue EC. Dashed line is without recurrent dynamics and solid line with recurrent dynamics. And you see here as well that in the EC, it doesn't really make a difference whether you use recurrent dynamics or not. Now we have modified the Rhodes model a little bit by adapting the sparseness and the connectivity in CA1 to more physiological levels. And then we get this graph, and we continue to work with this slightly modified, a bit more biologically plausible model where it actually makes a difference even in a C whether you use recurrent dynamics or not. Okay, so this is again the two plots that you have seen before, the correlation sort of in CA3 and in EC as a function of Q quality with recurrent dynamics and without recurrent dynamics. Now, you could also measure the performance of such a system in a different way, namely by saying, okay, what's the confusion rate? So what's the probability that the recalled pattern that you get is actually more similar to a wrong pattern than to the right pattern? So it's not so much about what's the quality of the Q, but how much do you confuse it with other ones? And if you do that, the performance looks different, then it actually makes no difference. Even in CA3, it doesn't make a difference whether you use recurrent dynamics or not. So this is with random patterns. Yeah. Now we thought, well, now we know a bit more about what the input into the hippocampus is, so we could do simulations with more plausible patterns. So we used grid cell patterns. We have simulated 4 modules of grid cells, and then the population activity at one particular location in space, right, taking over all these, then serves as an input to the entorhinal cortex, as an entorhinal cortex activity. And it's clear that this is now more correlated. There's more structure in it than random patterns, because if you take 2 nearby locations, then at least for the low frequency gratings, they will be highly correlated, right? So the pattern now has a different statistics. And this really has a quite significant effect on the results. So the same plots, maybe I go back 2 slides again. So this is with random patterns, and this is with these more plausible correlated patterns. And what you see, there's no difference anymore in terms of correlation. And in terms of the confusion rate, or so what's the probability that the correct pattern actually is the most similar pattern to the recall pattern, we see that the recurrent connections actually are harmful, right? So this is This is with recurrent dynamics, this is without current dynamics, and the performance without recurrent dynamics is better than with recurrent dynamics.
I'm confused. What are we supposed to be taking from these graphs? I mean, somehow you're saying that if they are the same, that means the system is working properly? It's a supposition? Or?
Well, first of all, so this is a Q quality, so this is what you feed into entorhinal cortex, and this is the correlation with the correct pattern, so that's what you get out. And if the whole thing works well as an auto-associative memory with the capability to to recall from a partial Q, then you want these curves generally to be up here, right? So that's the one message. And here you see the dependence on the Q quality. Now, the difference between the two curves is whether you use recurrent dynamics in CA3 or not. So either you use CA3 as a Hopfield network and you let it settle into its sort of attractor point, and then you go through it, or you don't do this. And so these graphs show that whether you use the recurrent dynamics in CA3 or not doesn't make any difference in terms of performance. And these graphs show that if you use the recurrent dynamics, actually you tend to confuse patterns more.
Right, and what do you conclude from that fact? The fact that when you use it, there's no difference? Or when you there's a standard framework which is head of a conceptual part, right? And the central idea of this conceptual part is we have a Hopfield network, and this Hopfield network helps us to complete a partial Q. So if you have a partial Q, we feed it in, then the recurrent connections are essential to recall the complete Q. Right, so is that arguing that model is wrong?
That argues that the model is actually wrong. I mean, it doesn't do that, right? I mean, what does wrong mean in a model, right? It just says that the main claim that the recurrent connections in CA3 are essential to do a good recall that doesn't work in this model. And it even didn't work in if you look at it carefully, I mean, this curve is pretty much the same as this curve. Even in the original Rhodes paper, it didn't work, right? And now, the additional thing that we say here is that if you use correlated patterns, it's even more severe. So the statistics is really different whether you use random patterns, which are sort of really favorable for a Hopfield network, or whether you use correlated patterns.
I have a conceptual problem. So when you talk about Hopfield networks and pattern, you mean the activity pattern of a set of neurons.
Yes.
When you showed the grid cell activation pattern, that was the activity of one cell in space, which is something different. I don't get the connection.
So this is the pattern of one cell across space. And we have a lot of these cells. And I said when I take the activity of all the units at one location, that's the way we get the patterns.
How are you reading out the cues for the feed-forward network?
How do I read out the cues?
A little bit, right?
How do I read out the cues in a feed-forward network?
They're corrupted after the feed-forward. The thing about Hopfield network is they go to point attractors. It's easy to read.
Yes. And in a feed-forward network, you put a pattern here, you let it propagate here, and then you have a reconstructed pattern. And in a heteroassociation, you train a network to do a mapping between one set of patterns and another set of patterns. And if you don't give the original pattern in the input layer, but a corrupted version, hopefully a good heteroassociator will still reconstruct the original pattern that has been used as a target, right? Wilshire model is a heteroassociation model that does pattern completion. So you can do pattern completion in a forward network. It's just you don't have the constraint that the input pattern should be the same as the output pattern. So you can associate any pattern to any other pattern. If you give a partial Q as an input, you get hopefully the complete Q out.
So from an experimentalist perspective, I would sort of ask, so if you took Jim's data,
Yes.
and you say, okay, those data are consistent with the idea that mismatches cause you to come back to the same pattern, does this network do the same thing? Because the space of networks is huge, right? So
Yeah.
it's really hard to sort of know whether we're in a space of networks that's directly relevant to the physiology or some other space of networks.
Yeah. I would have to think about this for some time. I mean, at least, so the first half of your talk, I think, would be completely consistent with this because the role of the intergyrus is the same. CA3 and CA1, I see some problems there, so one would have to think about this. But I think that a lot of this standard framework is so dominant that, every experimentalist sort of
pretty much is in this mindset, okay, so we interpret the whole thing in this way. And often you can interpret the data also in some other way, because, I mean, we are talking about a structure that's really deep inside, right? And often, I mean, in physiological data it's more direct, but sometimes even behavioral experiments are interpreted in these terms. And then it's not really clear, is this in CA3, is this in CA1 or so? So this is a thing really worth discussing, but I will take this offline now. Okay.
Can I have a quick question? What are these red dots there?
Yes, I'm going to. So now that we ask ourselves, okay, so why does this happen? So to get a little bit more into this, so at the red dots, we looked at the histograms of correlations, and that's what's shown here. So for this particular points, we see here in blue and cyan, this is, so okay, so one histogram shows in blue and cyan the correlation between the recalled pattern and the correct pattern, and in red, the correlation between the recalled pattern and the wrong patterns, right? And ideally, as you see, the correlation with the wrong patterns should be low, and with the correct patterns should be high. In blue, you see those cases where there was one wrong pattern that actually had a higher correlation than the correct one, right? And please notice, there are many, many more entries here than there, right? That's why, right? So this distribution, this is sort of to the power of 4, but this is just 50. That's why you have these blue, so many blue ones here. Okay, so this gives you an idea sort of what happens on a histogram level. Now I have to see. So this is with recurrent dynamics, this is without recurrent dynamics, and this is in CA3, and this is in EC. And what you see here is what happens due to the recurrent dynamics in CA3. The better patterns actually get better, and the worse patterns get worse. So the whole distribution just gets wider, but the mean value does not improve. And the consequence of this larger spread of correlations is higher confusion, because the left half sort of moves towards the confusion, the wrong correlations. Yeah? So this gives a little bit more insight why you have this apparent discrepancy, that there's no difference seen here, but there's a large difference here. Right? That has to do with the variance of the correlations with the spread. Okay. Finally, we have also simulated a network, and I should maybe go back to to this one here, where only these two connections are plastic, everything else is fixed. And when we want to associate patterns, we put a pattern here, and we do heteroassociation from EC to CA1 and from CA1 to EC, and the pattern with which we heteroassociate is generated along this loop. I mean, we use this loop now. I mean, in principle, you could just create random patterns in CA1, right? And then you could forget about all this. But this is sort of one way to create random patterns here. Yeah? And I mean, we believe, according to crisp theory, this is important for other things, but could serve as a seed for random patterns in CA1. So what we basically do is we put our patterns that we want to store here, create random patterns here through this pathway, do heteroassociation, and then at recall, we just use this heteroassociation back and forth. Right? So rather than having a Hopfield network, we have a two-stage heteroassociation. Okay. On the left side is random input. On the right side is the structured grid cell input. This is the correlation in EC, and this is the confusion, or the number of percentage of correctly retrieved cues. And here you see for random patterns, the correlation is not so great in EC. The correctly retrieved cues is sort of like in the other cases. But if you use correlated patterns, there's really a big difference. So the correlation is slightly better in this simplified model, and the correctly retrieved cues is much better. So actually, with this much smaller model, but just using two heteroassociations, you can perform as well or even better than the full model where the autoassociation happens in CA3. And if you use recurrent dynamics, it's even worse here. Okay, so this is the part about sort of crisp theory modeled with respect to associating just single patterns. So next I want to talk about storing sequences, and this is done by Jan Melchior, a PhD student in my group, again together with in collaboration with Sen Cheng. So this is our architecture that we use. So this is what you have seen before. We don't have a CA1 in this case. We can put it in, but it doesn't really make a difference in terms of performance for this sequence storage. So what we use as input is handwritten digits from the MNIST database. So that's a very convenient, well-known database. We train an autoencoder to compress this about 800-dimensional input into a 200-dimensional representation. So we take that as a EC representation. Then we have random mapping that's being trained also, but to map random patterns to random patterns to a 12-fold increased representation. You see this here. This is a large sparse representation. And we assume that we have an already self-organized sequence in CA3 of random patterns. And so this is 440 units here, and we've stored a sequence of 200 patterns there. So that exists. And then in the moment we want to store a sequence, we present the patterns of the sequence one by one to the input layer. They're encoded into this more random representation, then made sparse to orthogonalize them. And then these two connections are the ones that are plastic by a Hebbian rule, with some weight decay.
What is going on with the feedback from the input and the EC? What is happening?
From EC to input, that's, in the end, we want to visualize how good is the recall, and for that we need a reconstruction.
Oh,
so this is sort of mainly for us. It's not really.
Oh, I
right?
was wondering.
Yeah. Mm-hmm.
Got it.
Okay. So storage is clear. So we okay.
The hippocampus is really responsible for reconstruction because I don't know.
No, this is not. This is cortex. This is not part of the hippocampus. Actually, strictly speaking, this is not even part of the hippocampus, right? This is the entorhinal cortex, and this is the hippocampus.
Okay.
Right? And this is a very crude model of the visual system. Here, retina, right? And then sort of a one-layer model of the visual system. Okay, so these are the patterns that we store. It's just a random sequence of digits. And it's somewhat difficult insofar as you have very similar patterns in this sequence. Yeah? Okay. There are actually two slides. You don't see the difference because one is the input and the other one would be the reconstructed output by the autoencoder. So the autoencoder works well. Okay, so this is now, we present a queue, which happens to be this 3 here. And then, maybe I go back to the architecture. So we present a queue, it goes through this one, it triggers a pattern here, and from then on, we just let the internal dynamics run and hope that it actually has sort of started the sequence at the right position, and then we let the internal dynamics run, and then the feed-forward creates us an output, right? And that would be this one here. And if you compare this with the stored patterns, you see that it works fairly well, right? And what it does a correct recall. It doesn't do perfect. And I should mention, these are the patterns that have been stored last, and these are the patterns that have been stored first. So there's some degradation. It's actually linear degradation of quality as the patterns are sort of further in the past. Yeah.
Sorry, clarification. So if you're presenting that pattern, I don't understand how you get the first part output.
Yeah, okay. Yeah, very good question. We have a cyclic sequence of 200, and we start here, we let it run through, and then it continues there, and we let it run sort of for one full loop, right? So for ease of analysis.
So there is learning, right?
Well, right now there's just recall. The learning was before when we store the sequence, and that's important. Thank you for asking. So during learning, each pattern is only represented once, and there's one single learning step. So this is really one-shot storage of a sequence of patterns, right? And that's essential here, because usually models that use store patterns in the recurrent connections of CA3, they present the same sequence a couple of times, right? That's not necessary here. This is one shot.
What are the dynamics of the recurrent of CA3? How do you?
That's a normal Hopfield kind of dynamics. So.
But it's just generating sequences, or it's sort of exploring randomly.
Okay. So in our it's you have some activity, and that with sort of delay of 1 determines the activity of the whole network in the next step. So it's really just wandering around in state space.
But it's not sitting in one spot.
It's not sitting in one spot. No, it's generating a sequence.
Let's just train on one sequence, this sequence.
Yes, it's just a 200 pattern sequence. And if you continue training on more sequence, then you override, because the internal sequence only has a length of 200, so that's the defined, sort of by us defined capacity that you have.
Can we interpret so that some of the patterns become degraded, if I'm understanding correctly, if you move to the right on the top row, but then they get sharper again later. So am I seeing that correctly? Like, for example, the third pattern after the 3 looks pretty degraded.
Yeah, so actually overall the top level, top patterns are more degraded than the bottom ones.
Right, but I'm saying it seems to become more degraded and then less degraded later. That's a property of this network, is that it doesn't. Is that a correct?
Well, what's maybe important in that context is, so we have an intrinsic sequence in CA3, and that is very reliable. If you start at the correct pattern, then you really get the true pattern, the true sequence out. And it's very noise resistant, sort of. It's robust with respect to noise. So it really has a tendency to produce reliable. And from then on, this is sort of perfect. You can think of this as, the first approximation, perfect. And the reconstruction then determines whether it's degraded pattern or not. And earlier patterns are more degraded than later ones because it has been farther away, sort of more in the past that these patterns have been stored. The fact that it looks like it's right now more degraded, and then, so that either it's just an accident that this happens to be more degraded, could also be that in the CA3 sequence, you don't jump directly on the sequence, but somewhere else, and it needs some time to actually converge to the sequence. And that might also lead to this corrupted version, because this is not a reconstructed pattern. That's the thing that we put in. Maybe it becomes clearer if you move to the next one. So this is a noisy version, and then you see it's more degraded. So it takes a few steps until the sequence until the system converges to the really exact patterns on the sequence. It sort of has some distance to the sequence, and then it's converging more to the sequence. Yeah, we have to finish. Okay, I think there's nothing really very crucial. I mean, there are some errors. About 2% or so of the recalls are failures of the sequence, but otherwise it works. Yeah, and I just stop here.
So in the sequence generation, how would you decide when you have to decode?
Okay, so this is not an autonomous system, if you like, right? So we really by hand say, now you store and now you recall, like in most other systems. So so there's no intrinsic mechanism that decides whether to store or whether to recall. I mean, that's a problem with almost all models, most of the models, that you have to by hand, you distinguish a storage and a recall phase. I mean, my customer has a model where he interleaves that. There's more autonomous way, so we would have to combine this maybe with ideas like that in order to make this more autonomous.
So should I think of the sequence of 200 entries more of a sequence of 200 rather unique entries that might be very similar? Because if you use MNIST, this suggests that it's kind of a sequence where we sample from 10 digits, right?
Yes.
But that's not the case, actually, I assume, because you're
in the intrinsic sequence, the patterns are all unique, so there's no danger of confusion there. And now, if you have a pattern of unique, if you have a sequence of unique patterns, and then you can associate patterns that might be even really similar, and the sequence would still be able to retrieve that.
Say you have in the 200 sequence, like it's really just 10 different inputs, right? I mean, you run it through an autoencoder and orthogonalize. So this is kind of that's great. So if I had just 10 unique input patterns, right? Then feeding it once then should activate more positions in your.
Yeah, then it would by chance activate one pattern in the sequence, hopefully, and run from there. Okay. So whether you feed in this one or this then perfectly identical one, So you would have an equal chance of start the sequence here, there, or there, or so, right? But once it has decided that it starts here, it will reproduce the perfect sequence despite the repetitions. But here, it's actually the differences that you have between these two ones is sufficient to actually jump to the correct. I mean, the system does not confuse, for some reason, not these, but it confuses, I think, this with some other pattern or so. Okay. I mean, this autoencoder is very is able to distinguish these fairly well.
Yeah.
Mm-hmm.
So if I understand correctly, so you're saying when you did the two-step
heteroassociation, yes,
it works better than the auto-association
yes.
CA3. Do you have any insight as to why it's better? Well, why is that succeeding where the one-step auto-associator fails? What's the difference other than the architecture, but intuitionally, why is that one better than the other?
Well, it's known that the Wiltshire model has a sort of better capacity than the Hopfield network, but I would have to go into this and try to. No, I can't really offer a good intuition for that.
Can we say that the internal sequence is sort of like generating a bunch of hash codes? I mean, the patterns themselves are completely meaningless, but they're just but it's a very reliable machine to generate the sequences, and you're just basically gluing kind of pointers on by training what each of these completely reliable but random and meaningless patterns produces, then the thing you want.
Yes.
And that's a very robust way to do sequences. And I have to say, it's completely, to me, it's a revolutionary thing because people have been talking about, sequence learning as okay, you see A, B, C, D, E, and then the network learns to produce A, B, C, D, E. I mean, directly through recurrent connections. It is a very powerful metaphor that I think has gripped the minds of people for many, many years. So this is a very different way to do it. It would be nice to know why it works better. Is it just because it's just super hard to train sequences in this type of network quickly, reliably, or if you put in a sequence it doesn't like, you're kind of stuck, and so it only produces sequences that it likes to produce, and then it attaches your stuff to it. Really.
Yeah. We were just starting to do these. Andreas?
Any relation to pre-play?
Yes. So this is one of the arguments for the quiz theory, that it naturally explains the phenomenon of pre-play. Pre-play means that you can record from sort of sequences sort of prior to the experience. A replay is you put a red in an environment, and then later on the red replays the sequence of activity that it has experienced in the environment, and it's sort of interpreted as sort of re-experiencing what has happened before. And pre-play is the phenomenon that you actually find these sequences before they are experienced, which is a bit strange, right? Which is logically impossible in the standard model, but this one would explain this, because the sequences are already there, and then they're only used to associate patterns to it.
Okay, one last question.
If you want to associate onto this some sequential structure that's more interesting than a linear structure, like a T-maze type structure in space, where sequences could correspond to, and there's a join, how would you do it?
So the concept of the quiz theory is that that the purpose of the hippocampus is really to store sequences, linear sequences. Something that happens in time, and things that happen in time is always just linear, right, by definition. And if you want to represent more complicated structure, which is also in some sense connected, but not necessarily sequential in time because you split off, that would be something that's not done by hippocampus, but by more semantic structures.
Okay, fantastic. Thank you very much.